Hi, I'm Rainer, and this week we're going to be doing another rolling race. So, in this problem, we've got an object sitting at the top of the hill, and it's going to roll down. And those objects, the object that's going to roll down, you get a choice. It's either the sphere, the cylinder, or the hoop. And my question is, which one's going to reach the ground first? So, if we take a quick look at what spheres, cylinders, and hoops have in common, I can pull up their moments of inertia. And I can say, hey, they really look the same, except they've got this fraction next to them. And that fraction differs, and that's the only thing. But the rest of it is mr squared. So I might say, why don't I make a general object and give it a general moment of inertia, which I'll call b mr squared, where b is just that fraction. And when I do that, I can eventually look at the effect that b has on some other quantities and see what that says about the objects. So I'm going to apply the work energy theorem. I see some distances falling, I see some stuff rolling, I see some stuff speeding up, and I see a lot of stuff that I know the work energy theorem can handle. So let's do it. Let's say our system is everything. And when I say everything, I mean the given object. So not the sphere and the cylinder, there's only ever one at a time, but the object plus the earth plus everything else. And I know that work equals change in energy, and the changes in energy in this system should be something like delta K translational, delta K rotational, and delta U gravitational. So with that in mind, I know work done equals 0 because everything is in my system, and so I have no external forces. So I'll say 0 equals work, and then I know that this thing starts at rest. So I'm going to say V initial and omega initial equals 0. So keep in mind, we don't know anything about mass or radius of any of these objects. They don't specify. So we're just going to hope that some stuff cancels later, and I think that it will. So if we write this out, and just in terms of V final, like I said, we get a 1/2 m V final squared, and then we get plus a 1/2 I, which we're calling B mr squared, times omega squared, which we're going to use the rolling condition to say equals v squared over r squared. So I'm going to say v final squared over r squared. Then for delta UG, I know it has to look like mgh, and I know that since it's falling down, there's going to be less and less potential energy, so it should be negative. So I'm going to say minus mgh. And something looks really good right now. I notice right now my r's cancel, so it's independent of r. And also, if I divide everything by mass, my mass cancels. So it's independent of mass. And so we lucked out by using the work energy theorem because we don't have to worry about any information that we don't have. So let's look at this. We want to find out which one reaches the ground first. So I want to know which quantity in this equation has to do with sort of reaching somewhere first. And the only one that comes to my mind is velocity. So let's solve for velocity and see what we can say from that. So if I move the GH to the other side, let's multiply everything by 2, and then move it to the other side. So the halves go away, and that gets multiplied by 2, and the 0 stays 0. I bring over to 2GH, and then I say that equals VF squared, and I'm going to factor it out. I'm going to say this is a VF squared times 1, and that's a VF squared times B. So I'm going to say 1 plus B out here. And so if I solve for V final, I get something like this. The square root of 2GH over 1 plus B. And one thing you might notice is this is the V final for some given H. So for any given H, not necessarily the whole height, but halfway down and a quarter of the way down, at every single change in height, this V final is defined. And notice, it's dependent on a bunch of constants. And B only depends on the object. So I want B to be really small if I want to be fast at every spot. So if B is really small, I'm going to have the highest speed at any given height. And that, I'm going to make the argument, means that if you're fastest at every spot, you're probably going to reach the ground first. So I think that's thorough enough. And so we can say the thing with the smallest fraction outside of it, keep in mind 2/5, 1/2, and 1, the one with the smallest fraction is going to be the fastest downhill. So I claim that the sphere wins followed by the cylinder, followed by the hoop. So that's all we have to do for this problem.